Okay, welcome. Wednesday, December 16. This is our last class session. And right now, we have the exam posted online. We posted that exam last night, a little bit after 11:30. So I'm assuming you already have that with you. And the only purpose I had for today was to answer your questions or do problems you'd like to see done or check on. Not going to do problems related to the test, of course, but if you have problems that are similar that are in the book, I have no objection to doing those with you. Let me get someone else going in the room here. Okay, so you can just type things into the chat or you can speak them out loud. I'm in a different room today, so I don't have awesome audio or bandwidth. So I don't mind if you speak them, but you could also type them in the chat and that should be pretty foolproof. But you go right ahead. Other than that, I'm just sitting here doing work and cleaning up papers, so you can just hang out as long as you like or not hang out, ask questions or not ask questions. This is all up to you. Let me check that out. Thank you, Austin. Let me pull up the question and we'll just look at it and see if I can name something. You're not always able to pinpoint things, but let's see. So first of all, I'm going to pull up the test on a different screen and then I'll share that window with you. Exams, exam 2. Is this exam 2? Yes, it is. Okay. So find the exact value. Okay, I can. Let me share this question with you so everybody knows what we're talking about. And then I think I can find questions similar to it. I think I know what section this is from. So first I'll share the screen with you and then I'll pick up my book. So I'm sharing the screen and basically you're described an angle and you're described the angle 2x. So you have information about the angle 2x. The cosine of 2x is -3/7 and 2x is an angle between pi and 3 pi over 2. That's what the question says. And then they said, from this information, can you state the exact values of sine, cosine, tangent, cosecant, secant, cotangent? So the exact values of all 6 functions. So before I open my book, this is the first thing I notice. We got x, we got 2x. So I'm thinking I'm going to go looking in the sections that are like double angle formula. 2x is double x, or half angle formula. X is half of 2x. So in those sections, and I'm just consulting my index. This is after some basic identities. I'm looking at section 5.2, 5.3, 5.4, 5.3, and 5.4 are double angle and half angle. When I find something, I'll put it under my camera. But I'm just kind of looking. I mean, it's going to be this general area, 5.2, 5.3, 5.4. And I'll tell you this, often in the book, he said, here's this, give me one function value. But we often said, if you got one, you can get all 6, right? So that's why I asked for all 6. Here's an example from section 5.3. Now I'm going to move back to my paper and share under my camera. This is not the problem you're doing, but it's similar. It says, if I tell you about sine A, can you tell me about sine 2A? Okay, so that's double angle formulas. I'm just going to page through there. The next section is half angle formulas. Let's try one there. Here's an example, similar, not the same. If cosine of A is 3/5 and A is between these two values, can you find the half angle? A over 2, A over 2, A over 2, tangent, sine, cosine. Might as well do the other 3 too. Now remember, your problem doesn't use the letter A, but it certainly says, here's 2x, can you find the values for x? So I mean, that is a very similar problem. Let me see if I can name you another one. Example 2 in that section is similar. Let me write these down now. So for anyone who's not available just right now, sometimes they read these notes or videos. So let me save this question for anyone else. It seems like 5.4 is slightly closer to this. And the examples I just showed you are examples 1 and 2. And how about problems? And then I'll get back to the chat window, make sure I'm covering your thing, but I'm just writing right now. Problems, oh, many of the problems in section 5.4. I'd say the problems from 1 to 18 are all similar, not the same, but similar. Let me get back to my screen so I can see your questions. Oh, who knows what's going on here? There's a different room. That's thanks to Austin's comment. Austin said, it sounds like hibachi grill in the background. Okay. Does that satisfy your question, Castillo and Austin, that you see where it comes from now? Got a lot more street traffic here. That's probably what you hear. Is that, I'll let you give back to me. Let me get someone else in the room here, sorry. Okay, got Gabe in the room. So is that a good lead on that, Austin Castillo? $5.32. No problem. Let's do it. And anyone who has other questions, you just put them in the chat window. We'll take them in turn. We'll just take them in order. 5.3 question 2. This is 5.3 question 2 in my book. It says this statement blank an identity. And they're asking you to fill in the blank with is not, true, false. So this statement true is true in identity, the statement false in identity, forget that. This statement, is it an identity or is it not? I recognize this, you recognize this from your formula sheet. as the identity for the cosine of 2 theta. That is a legitimate identity. Oh, okay, the next two. Sorry. Thank you. Okay, that's better. Now I understand. I was curious why you were picking that other one. Okay, let's do this. My fault. So it says the sine of A is minus 3/5. And it says A is between 270 and 180. And it says find cosine 2A. Okay, I'm about to do that. I always like to draw a picture of angle first. So let's think about, and they're working in degrees, be comfortable in degrees or radians, of course. But this question was asked in degrees between 180 and 270. Here we are on our paper. A sine ratio of 3 to 5 with a negative. In this quadrant, sine is negative, yes. And the sine 3 to 5, that's the vertical, the y coordinate over the hypotenuse. So I'm just going to pick, I'm not trying to draw it super accurately. I think this is even too tall. I think this is too tall, and I don't think it's a good drawing. But let's follow through, because then you say to yourself, even if your drawing's not perfect, I'm still going to be okay. So I have y over r is minus 3 over 5. The y coordinate is negative, even though I labeled that side with a positive 3. This is the angle A, because they said A is between 180 and 270. I need to find the x coordinate now. So Pythagorean theorem, 5 squared equals x squared plus 3 squared. I'll let you work that out, but x squared plus 9, x squared equals 16, x is plus or minus 4. This length is 4, but I'm in the third quadrant, so I say the x coordinate is negative 4. Do you see now what I meant by my drawing is not good? Of course, 3 is not bigger than 4, but I'm still in the right quadrant. Even if my drawing's not beautiful, it's still fair. Let's see if we can still keep it. So now I need the cosine of 2a. Now, I know 3 identities for the cosine of 2a. They're all on your formula sheet. One of them was from that vocabulary problem we just did. Cos squared a minus sine squared a. Another is 2 cos squared a minus 1. Another is 1 minus 2 sine squared a. You can use any one of these 3 identities. They're all going to bring you the same answer. And from this drawing, I know the sine and cosine. I don't matter which one I'll use. Why don't I use the first one? So let's read the cosine of a and square it. Cosine of a is minus 4 over 5. And the sine of a, remember, was given to us as minus 3 over 5. So now I'll just do my arithmetic here carefully with the minus signs. 16 over 25 minus 9 over 25 is 7 over 25. Now, it might be nice to look at where 2a is based on what a is, but I've done what I was told to do. The only reason I'm going to do more is because this is the way I phrased it on the exam, although this is not the same problem as your exam. Do you see that if A is between 180 and 270, then where is 2A? 2A would be between 360 and 540. So 2a is in here. Because I just doubled the 180, 270. But I just calculated the cosine was 7 over 25. Positive cosine, that means here. This has got a negative cosine over here. So let's say 7 over 25. That's going to be relatively steep. 7, 25, adjacent over hypotenuse. Positive 7, y coordinate is positive. What's that y coordinate going to be? Oh, my goodness. 25 squared is y squared plus x squared. 625. Y squared plus 49. Subtract 49. 576 is y squared. Something about 576 rings a bell. I think that's maybe a perfect square. I'm just going to pull up my calculator. It's not on your screen. 576 is 24 squared. I have to say plus or minus 24 algebraically, but in this drawing, you see that I'm in the first quadrant, the y is positive. This must be the angle 2a. And the reason I drew this for you is to reemphasize that once I draw this angle, I can find out any function of 2a, right? Cosine, sine, tangent, secant, cosecant, cotangent. Once you draw the angle and label all the sides, you have all this information. Cosine is 7 over 25. I'm in the first quadrant. Sine is 24 over 25. Tangent is 24 over 7. Secant is just a reciprocal of cosine, so that's 25 over 7. Cosecant, reciprocal of sine, is 25 over 24. Cotangent, reciprocal of tangent, is 7 over 24. In the book, he created this problem with, kind of nice numbers. So this wasn't hard to write down. No rationalizing denominators, no square roots, really. And your problem, exam 1, was about half angles. This problem is more about a double angle problem, but this is not a bad example of the kind of work you're going to do. Okie dokie. So that's a good question. And I'll start numbering my papers. What other question can I help you with? You're looking in 6.1. Okay, let's look at that. Thank you, Julia. Let me pull that up in my book. 6.136. I got it. Okay, that's a good problem. This is similar to an exam problem, so it's a good practice. .1 number 36 says Find all solutions. Zero degrees, theta to 360 degrees. Sometimes people leave off one of these equal signs, not the other. I don't think that's a major problem. I always consider both the endpoints in there. To the nearest tenth of a degree. Now there's an indication right there that maybe this won't be a happy, sweet angle, that I'm going to have to approximate something, right? So the equation is sine squared theta plus sine theta minus 1 equals 0. This is a quadratic equation, really, if it wasn't for the sign. So the first thing you should think when you look at this is, if that was just an x squared plus x minus 1, I would think of this as an ordinary quadratic equation. Why don't I just think of replacing the sine theta with u? And this is the technique that they're demonstrating in this section. So first, let's just focus on the quadratic equation u squared plus u minus 1. I wrote sine squared is u squared, sine is u, 1. I just physically replaced it. Now, if this quadratic equation factored, I'd totally be up for that. But this doesn't look like it's factoring. No matter, I'll pull out the quadratic formula. So quadratic formula is always useful. In this problem, remember you respect the signs. A is 1, B is 1. Remember C is minus 1. You have to respect the sign of every number. So now let's find out what u is. I'm using this formula. So I say the opposite of B plus or minus B squared minus 4 times A times C divided by 2 times A. Let's add some color here. B is 1, 1. I can add some color. A here is 1. C is minus 1. Don't lose that minus sign. I can add some color, but it doesn't look like I added much variety since everything is 1. Now let's clean this up. Negative 1 plus or minus 1. And 4 times 1 times 1 is 4. Notice this is a plus sign. Minus 4, 1, minus 1. This turns out to be plus 4, right? Over 2. And there's really no thing to clean up right here. Minus 1 plus or minus square root of 5 over 2. Those are my two answers for u. That's just u. Remember, I'm solving for theta. So I need to replace the u. Let me write down my two u's here. And now I'm definitely going to have to use a calculator. So I need to replace u with sine theta. Sine theta is minus 1 plus root 5 over 2, or sine theta is minus 1 minus root 5 over 2.
Oh, the steak was so good.
So my job is to discover what theta is here, right? I'm trying to figure out what theta is. And don't overlook this, that I've been told what the sine of theta is. I've been told what the sine of theta is. And when I think sine of theta, I traditionally think y over r, right? So I've been told a triangle here and here. It's not one I recognize, these are odd numbers. But first of all, on my calculator in degrees, I could ask the calculator what angle has that sine. I could ask the calculator what angle has that sine. Before I do it, I think I'm going to try to draw these. I want you to also notice that the square root of 5 is about 2.2-ish. So do you see -1 plus 2.2? This number is a positive number. This number, -1, -√5, definitely a negative number. So let me try to draw these, and then I'll approximate on calculator. Sine y over r. I could think of the 2 as the r, possibly. I could estimate this -1 plus 2.2, just estimating. This would be about 1.2 to 1. And notice that is not 1 to 2, but that's almost sorry, I need to get my paper above the screen. Remember, just keep this in the back of your mind. That's about 1.2-ish, very roughly. That's almost 1 to 2. That's almost 30 degrees, but it's a little taller. So I suspect this is a little more than 30 degrees. But I also can draw this angle over here. And it would have the same height, same y, and the same radius. So this is the angle theta here too. I need to find out what the angle this is from my calculator now. I mean, that's the next step. But what I've drawn here is really important. There are two angles that have that sign. Down here in the third or fourth quadrant, sign will be negative. But up here, sign is positive. I'm going to ask my calculator. I do not have my calculator handy, so I'm just using my calculator on the screen. You know what? I don't think you should overlook this. I'll share this with you. Desmos you can use in a pinch if you have access online as a calculator. So I could say, I could ask calculus, or I'm sorry, ask Desmos, what is the sine inverse of -1 plus square root of 5 divided by 2? I'm just typing that in. Let me share that with you. Now, that is not a little bit more than 30 degrees. So I'm guessing I'm in radians right now. Let's go to Desmos. Let's talk degrees. Okay, now I am sharing that screen with you. You see that this first answer right here is about 38, and we were supposed to go to the nearest tenth, 38.2 degrees. Now that would make this 180 less that. So what's 180 minus that number? You can do that yourself as well, but 141.8, if you want to do a safety check. These are approximations, so I tell you that they're approximations. But that's two answers. Now let's draw the other two answers. I'll go back to my paper, but you have the program. You have the idea here. So let me draw the other two answers relatively quickly. Now, these are not the same angle upside down. Think of -1, -2.2 as to be almost maybe a little more than -3.2. And then I'm in serious trouble. So this is a good problem. Why am I in trouble? -3.2 divided by 2, about, even if it's only an approximation, this is about -1.6. What's the problem with that? The sine is never that small. Remember, basically sine and cosine are always between -1 and 1. If you asked your calculator for the sine inverse of this number, the calculator would say error. So I have two legitimate things to pursue, but this branch gives me no answers. There is no such theta. So that means the two answers I found here are the only two answers possible. So final answer, theta is approximately 38.2 degrees or 141.8 degrees. That's not a bad problem. It's similar to yours, not the same. You have a problem with tangent in it. Always be sensitive to a problem like this. Never listen to anybody who's trying to tell you the sine of theta is 2 or the sine of theta is bigger than 1. Well, that's impossible. Likewise, the sine of theta cannot be less than -1. Okay, good. I really like that question. Thank you, Julia. Okay, so anything else? I can't fit that all on one piece of paper. I'm sorry, on one video screen, but remember, I scan these and post them afterwards. So if you want to look at the whole piece of paper, you can check that out later. What else can I do for you? That's a pretty good pace you're setting there. Yeah, just so you understand, my screen's not frozen here. I heard an interesting news story on the radio the other day saying, like, everybody says Zoom meeting is not as good as in person. And you totally believe that, and you understand that, but the story was about exactly why and how, and just how much you concentrate on visual and verbal cues when you're talking to someone. How much when you're talking to someone you're actually like singing together, taking turns, etc. So Austin has another question here. So when you're doing that, it's like when you're face to face with someone, you're kind of performing. There's no lags, there's no talking over each other. It's extraordinarily efficient. So we're just making do here, and that's okay. Austin's asking about the fourth problem on the exam. Find the sixth roots of 8i. The sixth root of 8 cannot be simplified. So are we allowed to leave it as that? You're asking me a direct question about that, so I'm going to answer you indirectly. Let me give you an example. Without giving you that example, let me think. Here's a really good example. Similar to what you're asking. What if I asked you what the fourth root of 4 was? Closer to what you're doing in these problems, where we write the fourth root as a 1/4 power. Now, I understand that fourth root of 4 is not a nice number. It's not a clean number like 1 or 2. But I do want you to consider this. That does not mean you cannot simplify this. So you should always look for ways to simplify. Let's talk about 4 as being 2 squared, right? And 2 squared to the 1/4 power, your algebra class, when you raise a power to a power, you multiply the powers. And that is 2 divided by 4 is 1/2. And now if you're willing to think about roots as powers, like 1/4 power is the fourth root, 1/3 power is the cube root, 1/2 power is the square root. Then what you're saying is the fourth root of 4 is the square root of 2. And the square root of 2 is still not a pleasant or simple number. But have I made this simpler? I would say yes. I would say that's a legitimate simplifying. If you would have left the problem as fourth root of 4 or 4 to the 1/4, would I object? I wouldn't object strongly. 1 point out of 10, maybe. 1 point out of 15, maybe. But you definitely should always look for perfect powers and things like that. I'll illustrate this on Desmos in a second. Now, that would not excuse you from a situation like this. What if I had the fourth root of 32? Well, then you should understand that there is a perfect fourth power right there, 16. Something like that, where you have a perfect fourth power inside. Inside the fourth root. Yeah, that is an obligation. You must simplify. But this is not in that category. There's no perfect fourth powers inside there. Now, you say, wow, really? Really? So I'll just pop this into Desmos just to show you that the fourth power of 4 is the same as the square root of 2. I am on a much smaller desk. I'll tell you the story later. But I'm kind of cramped right here. So excuse me sticking my arm obscurely under the camera. Screen share. Here's the fourth root of 4. That number kind of looks familiar, actually. Here's the square root of 2. You see it's the exact same number. These two numbers are the same. So just to make sure I finished Austin's question here, and then I'll get to Trevor's comment. This is not exactly like the problem you're doing, but it's close. Well, this might give you a clue as to how you could clean up that problem. Section or sections would number 4 be in? Trevor's asking. This is, I'll pull it up in just a second, relatively recent. I'm thinking it is problems in section 8.4, roots of a complex number. Let me put that under my camera with everybody seeing the same screen. There. Trevor's question, what section is this problem from? Definitely section 8.4, roots of a complex number. And you'd see problems like 3 cube roots of -1, 4 fourth roots of this complex number. This is page 390, but I'll just point you to the section. These are the instructions for taking roots like that. Is there one even closer to your problem? You know, several problems close to it in the examples and the homework. So just to make sure everybody's on the same page, especially if they are reading this or following this elsewhere. Let me make sure I'm referring to the right question when I say question 4. No problem, you're welcome. I just want to make sure I'm documenting this nicely for the other people that may be checking this later. So back to my paper. Okay. Good? All good? So, want to do something similar to that, that's fine with me. Or if you have another question first, that's fine with me too. And remember, you have an instruction page and you're signing the instructions, you're following the instructions, you're acknowledging the instructions. But basically in the instructions, I said, you can use any part of your book, any part of my website, any of our notes or videos. So in no way am I trying to block you from finding the questions, or I don't mind if you see the book, see the other questions like it and practice and try it out. I'm not trying to hide the questions from you in any way. So again, I'm not trying to be pushy. You just take your time, do things at your pace. I just want to make sure you know my screen is not frozen or anything. Excuse me. Uh, let me investigate Castulo's question, and then Austin asked a question. Oh, yeah, I like Austin's little handout a lot. So I will pass that on to everyone. But Castulo writes, I thought we could ask questions directly from the XYZ homework, but they are closed. Now that I've been in the XYZ homework last night. Let me just pull it up on my screen and see if they are closed, chapter 7 and 8. Okay, thank you. That might help me fix it if something's wrong. So let me go to XYZ homework. I'll pull up the screen in front of you too. So let me share the screen in front of you and see what we can find out. You see the screen in front of you. Last night you did 845, 86. And chapter 7, chapter 8. Yeah, I know for homework they were available until a certain day. But what I'm nervous about, what Castula's saying is, did the system close this course? And I don't think so, but let's find out. Calendar. Got it. Manage. Tag, details, events, messages, forums, rosters, gradebook, calendar. I hadn't even considered that. Let me, and maybe I'm looking at things here that you do not see. So I'm trying to find out if like the course date closed or something. Don't see it yet. Assessments, forums, blocks. The thing I'm most worried about, Castula is asking, is, let me check what you typed in there. Okay, so the first thing that means is that they're closed, like you can't do them anymore. You can't do them for credit anymore because they were due last night. But I'm trying to decide. I assumed after you guys finished sections that you were still allowed to practice inside them. That's right. I assumed that you could do them for review. Thank you. So I've got to find some button that says you're allowed to do these for review. And right now, on the top of my head, I don't see it. But I know where I can go to get the answer from a person. So I may have to investigate that right after class is over and turn those on. So, Castula, if you can just help me for a second, you're saying that you can access everything for review except 7 and 8. Is that what you're seeing? Okay, good. And everyone else, if you're nearby the system, are you all experiencing the same thing? I think I know the question I need to ask, but I'm going to have to ask one of the tech people behind the scenes. I don't think I'm going to solve that by course settings, and maybe even here, course settings. Availability and access. Available to all students through December 21. That's what I had expected. So I assumed, like it says right here, available to everyone through December 21, but I bet you I know that why 7 and 8 are different. Okay, but this is going to take one of our tech friends in the background. I will check this out as soon as I get out of the session. And I could say I might have this turned on based on other appointments today. Maybe by sometime tonight, I think I could have that fixed. Pay attention to that, and I'll send out an email when I fix it. I apologize that that is not fixed right now. Okay, in the meantime, I'm going to share this document that Austin shared with me. So this is not here or there. It's not the most important thing in the world, but it's kind of handy. I like what he has here. So let me throw that in the file sharing. Downloads, got it, file. And then I'll open it up in front of you and explain. So if it's useful to you, go ahead and use it. If not, if you don't need it, that's okay. So I put a file, which is just an image, inside the chat. And you can click on it and download it. But I will open it up as a window in front of you right now, just so you can see what I'm referring to. Well, it's very tiny type, so this might be tricky. Let me see if I can make this larger. What Austin's found here, and it's just a little more filled in than one of the sheets I gave you, is basically, let me blow it up again. Got it, minus. Must have found something from the watermark on the back says math box. And this is the exact values of sine and cosine and tangent and cotangent and secant and cosecant for every 15 degrees. So it's kind of cute. I like it. It does match the ones that I gave you, even in the 15 degrees, root 6 minus root 2 over 4. It just presents them factored in a slightly different way. Okay, I don't mind that. But it wouldn't be bad if you were looking at exact values and you calculated something and you matched it against this table. So they are not trying to approximate in this table for you. They're trying to give you the exact values. It looks like when something is undefined, they put a little dash there. The cotangent of pi is undefined. That's true. I would rather, but I'm not going to criticize someone else's work. I'd rather they wrote undefined instead of these dashes, but that's okay. I think it's still a useful table. If you want to print that out, you could write undefined on that. And it looks like, I'm going to clear that writing. Looks like they went all the way here to, oops, clear writing, stop scribbling. Looks like they went all the way to 360. Even to compute degrees and radians, you should be able to convert back and forth, but sometimes you might forget what 330 degrees is, 11 pi over 6 radians. So I think that's useful. Thank you, Austin. If you like, you can download that and use that. It's kind of a secondary reference. On our page, let me show you on our website where you could find something similar, 121, in our handouts resources, and then I'll catch Julia's question there. Handouts resources, formulas, right circle, unit circle. It was this handout where I didn't do exactly what they did, but I did sine and cosine for every 15 degrees, and then told you to fill in the rest and gave you a couple of examples in the second, third, and fourth quadrants. So not organized in the same way, but this handout has kind of the same information. Okay, or similar information. Let's go back to these other questions here. We'll go back to my paper. Exam 5, a question, exam problem number 5, Julia asks, and a question about number 3, Trevor asks. Let's show you exam problem number 5. And in a way, I cannot say to you that it came from a particular section. I mean, I didn't pick everything, was just from a section. Let me get that exam paper back in front of everybody. Come on. Here we are. Okay, so now you're looking at the exam again. Get that window so I can adjust it. And exam problem 5 is a Ferris wheel. So I don't know what I want to say about this problem, because I kind of put commenting on the problems themselves somewhat off limits. I'll say this first of all, and I can point you to a section where there are things like this. But I'm not going to say that this problem came from any one section. I do want you to understand this, that even throughout the book and from the very early part of the book, I can't tell you, but you could go back to nearly the beginning. For some reason, Charles McCaig is a very nice fellow, wrote the book. He just loves Ferris wheels. And he constantly put in the book, he even said, I love Ferris wheels. So he was constantly putting in the book problems about Ferris wheels and their motion in a circle and triangles. So his opinion was that inside the Ferris wheels, problems about motion, that there's just triangles, triangles, triangles everywhere, and sine and cosine everywhere. And so he just thought it'd be a fun way to do problems. Now, what section of the book was I thinking about when I came up with that problem? I think I can point you to something. Trigonometric equations. I'm looking in chapter 6. And for example, I'll give you one example, although I don't know that's perfect, but it's similar to this problem. So let's document this question for everyone. And there's part of this I want you to use your own creativity on. So the problem, I'll show you this section. But the Ferris wheel problems come from many sections. But I want you to pay attention to at least this one. I'm looking at section 8.4. Example number 5. This is one of his written examples, and maybe he's got some other problems too. Let's start with this. Let me put it under the camera for you. And then let me share my camera. And if you want to come back to this picture, we will. Okay, this is section 6.4, example 5. And it says, here's the London Eye. It's a Ferris wheel, it's so high, blah, 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 blah. These are the words that I would say are closest to the problem you're asking. Well, there could be more than one way to do this problem. So from the triangle in the picture, I'll show you the picture, you can derive parametric equations for x and y in terms of the parameter theta. And when you do this, you will get the position of the rider at any time after they start the ride. And pay attention to his comment, which is different than anything we have done previously. So when you're looking at exam problem number 5, your first reaction is, I haven't done that before. We haven't done that before. And the answer is yes, in a way, but this is similar. And he's trying to warn you right here. Yes, you haven't done this before. It is different than anything you've done previously, but this is not only useful, but you got to also think about the concept that you will do things that you have not done before. Now, I'll let you work through this problem yourself and so forth, but what he does is he gives you this triangle DBC, which is right here. And he says, you can use that. And he shows you how to use that to work out. This is what he called the parametric equations of the person riding this Ferris wheel. These are parametric equations. Thank goodness this is my book, or else I'd be in trouble for writing in it. I don't think it's wrong to write in books. You know, you want to make your own notes, it's your book. And so they can tell you, this tells you in this picture, the coordinates of this point you're at any time. Now let's go back to the exam problem. So this is a very good example. You don't have to do the problem like this, but you could. And with those two equations, he can create graph of X and Y, the position you are at any time. For example, this is the height someone is at any time on that Ferris wheel. The person on the Ferris wheel never goes below 15 feet. That must be the bottom of the wheel. The person on the Ferris wheel never goes above 135 feet. That must be the top of the wheel. But they can tell every height that that person's at. And this is the X and Y. And remember, the Ferris wheel is like the center. And as you go around, sometimes the X is negative, sometimes the X is positive. So the X could be, position could be positive or negative. But these are the two graphs of that. Now, you do not necessarily have to get that fancy to do that problem. But I would say this example is not a bad problem to look at. Now, I want to, before I go and see if that helps you or not, let me see if there's any questions in the problems that did that. He does have two in the problems from section 6.4. He does have two problems that are a little bit like that. But we're going to go back to the test question in a second. Let me see if he has others. So see also problems 33, 34, section 8.4. I don't want to comment on the test question per se, but I'll go back to the picture and say one more thing. Trying to find a good place to put this book because my table is too small. Let's reshare the test paper with you. So let's imagine this. The problems that I just showed you were telling you the X and Y position of any point on this wheel. So let's say, and this is going to be too much, but let's say right here that you knew the X and Y position of that red dot. but I'm not going to give you any numbers. I'm just saying it's got some numbers. So it's a little bit, apparently it's a little bit past 35 on the X position, and certainly a little bit above 50 on the Y position. So if you knew those two numbers, X and Y, could you, on another color, I want to make sure I'm drawing the right thing. Could you tell me how far that is? And the answer is yes. If I told you these two numbers, you could tell me how far that is. That's Pythagorean theorem. Well, it's Pythagorean theorem, but it's also just the distance formula between 2 points. So your question in this book, in this problem is, I don't want that. Find the 2 points that are 75 feet away from this anchor at 35. I'll say one more thing, and it's too much. Do you see the distance between these two black points is 70? Because one's at minus 35, 0, and the other's at 35, 0. Well, definitely the distance between those two black dots, those two anchors, is 70. So take the blue arm that I just drew and swing it up onto the circle. In fact, if you could swing that blue arm all the way up onto the circle over here, would these two dots that are blue be 70 feet away from the anchor? I think it's quite reasonable that that could be about 70 feet away. So what I'm trying to get you to visualize right now, I don't want to use blue because I don't want to connect it to those two dots. Can you imagine the dots that are 75 feet away? I think you could. The question is asking you to find them, not believe in them, but to find them. So in some sense, I think I went too far here, because not too far because someone's trying to help. I mean too far that when you give people hints, sometimes they blindly pursue those hints and they can only think about those hints, and that blocks them from thinking something else. I'm not trying to block you from thinking anything, but with the example I showed you in the book, with this kind of thinking, it is very believable that you can find the points that are 75 feet away, wherever they are. So that's the best assistance I think I can give you. Let me go back to our paper. Okay. I'll get to Trevor's question too, but is that too vague, Julia, or gets you in the right direction maybe? Everybody has the same question too, so anybody can chime in if they want that to be more clear, but certainly, yeah, no, you're welcome. Everything helps. Trevor's most recent question about problem number 3, how do you know if there's more than one triangle in a problem? I can give you an example of that very basically. So we'll pull up equation 3 in a second, but Trevor, in a sense, is asking about what the book calls, what people often call, the ambiguous case in the law of signs. And my suggestion to you is to remember the analogy I gave you with a crane. Let's pull out the problem so everybody's on the same page, and then I'll remind you what I meant by that. So remember the crane analogy. I mean a construction crane, not a bird called a crane. But just to make sure we're all on the same page, let's look at the problem that Trevor's referencing. Here we're back to the exam. And problem number 3 is right here. So this is a problem much more like, let me get rid of that stuff. Got it. Let me blow that up slightly. Got it. So here's a situation. I'm describing a triangle to you. And maybe this triangle doesn't work at all. Maybe there's 2 ways to draw this triangle. Whenever you're using, and it's not too much for me to say that this problem is a type of problem you saw in the sections about the law of sines and the law of cosines. But let me give you this example. Let's say that I was on a level ground and I call this point A. This is what I call the crane analogy. And let's say that the angle at A was, let's even make it an ordinary angle, like 45 degrees. So do you see that I drew that exactly 45 degrees? 1 over 1 up, 1 over 1 up, 1 over 1 up. So anybody without any protractor even will accept that that's 45 degrees. So this is my crane. And let's say that this is 100 feet. Let's just pick a round number, 100 feet and 45 degrees. Now, in the concept of labeling triangles, let's call this B and C. And you remember we were taught to label the opposite side to the angle with a lowercase letter. So I don't know the angle C, I don't know the angle B, I don't know the side A, and I don't know the side C. But in a sense, Trevor is asking, could there be one or more than one or none triangle here? Well, let's say that I told you A was 10. What happened to that picture if I tried to tell you that A was 10 feet? I almost don't even want to litter this picture with such a silly idea. Think about this, 10 feet? No, not if that's 45 degrees, not if that's 100 feet. You imagine that 10 feet might get you, if this is 100 feet, 10 feet is 1/10 of that. 10 feet might get you that far. There's no way this side is 10 feet. You would respond, ridiculous. Maybe I could even get on the television show with that. My kids would tell me that's not what that show's about, Dad. Is it ridiculous or ridiculousness? So what am I saying? That if I dropped a rope, now let me try to be not so ridiculous. What if I dropped a rope of 60 feet? Would that 60 feet be enough to hit the ground? 10 feet is ridiculous. There is no such triangle. But if I made it sound better and called it 60 feet, is that equally as bad? Maybe that would fail too. So how am I going to know if that fails? And this is going to answer Trevor's question, so be patient. What I should do is try to imagine how tall that crane is. And I don't have to imagine. In fact, I can calculate because this is a right triangle. If I drop the rope straight down to the ground, that's a right triangle. So what is the sine of 45? Vertical over hypotenuse. So I could say the sine of 45 degrees is h over 100. And that allows me to calculate h, even to approximate h. Now, sine of 45 is the square root of 2 over 2, or 1 over root 2. You could say it either way, but 50 root 2. And if I ask the calculator what 50 root 2 is, I'm just going to ask my own personal calculator. I'm not putting it on the screen. Calculators say 70.71 feet. Now here's how we're going to answer Trevor's question. So how about side A being 60 feet long? Again, you say ridiculous because it has to be at least, any rope I pull from C to B has to be at least 70.71 feet, a little bit less than 71 feet. 60 feet is too short. 10 feet is too short. 60 feet is too short. Now, Trevor's question was, in a sense, could there be a too long? What if I said to you, rope is 80 feet? Now, you know that this height is 70. If I give you an 80-foot rope, you could stretch it two ways. You could stretch that rope this way, call it 80 feet, or you could stretch that rope this way, call it 80 feet. What did you just do? You made two triangles. I could stretch that rope either way. So I could create a triangle that looks like that. I'm not drawing it too neatly. Or I could draw a triangle that looks like that. And they both could have my 45 degrees, and they both could have my 100 feet. But there are two possible triangles. So this is what Trevor asked, I think. You can say yes or no to that if you like. How do you know if there's more than one triangle in a problem? This is the example that tells you. If you, now your problem's got different numbers in it, okay? Well, that's fine. But if you imagine that crane at a different angle, different length crane, you can tell me how tall the tip of that crane is from the ground. And then when people tell you how much A is, you can tell whether it's too short or too long or just right. So I don't want to give you a math formula answer. I want to give you a picture answer like that. I think it's safer to think in a picture answer. I think that's really what you're asking. And tell me if it's not. I'll go one more step. What if I said the rope was 120 feet? Here's 100. Here's 45. What if the rope is 120 feet? Well, I cannot squeeze that under here. I have to like pull that way, way out here. 120 feet would force me to have one triangle way out here. I can't go 100 feet here and then go 120 feet this way. That's silly. That's not a triangle. Okay, how's that? Yes, that table on page 334 is useful. And you could say that the table on page 334 is like a picture or is like a math formulas of what I just said. That's good. Okay, here's what I'm gonna do. I have got to go figure out what Castillo was asking because that was a really important point. I think I can figure that out and I think I can get it fixed by early this evening, but you're welcome. And we're going to cut it off right here. You know, you can still send me questions. I don't mind that at all, but I'm not going to give away a lot of stuff here. I mean, I think you have what you need. I think you know what you're doing. So just write these things up as neatly and nicely as you can. If you have any weird disaster problems, you send me an email and let me know. Always better to fix things before the test is handed in than after the test is handed in. Okay, so you guys have a good day and get your test in. I'll be in contact with you after the test. You can still ask me questions after that, get your grade report and everything like that. But you guys have a nice day there. I'll talk to you later.